Yeah, apologies about that cut. We can go on from here. So yeah, singular value is u sigma v transpose or v conjugate transpose for a complex thing, and we see how it's just a way to represent any linear map from any space, like represented in 3 steps. For implement, first apply the v transpose matrix, then apply the sigma matrix, then apply the u matrix. Okay. So existence and uniqueness of SVD. Theorem: every matrix has a singular value decomposition. Every matrix has a singular value decomposition. Furthermore, the singular values are uniquely determined, and if A is square and the sigma j are distinct, the left and right singular vectors are uniquely determined up to complex signs. That is complex scalar factors of absolute value 1. Proof in Trefethen and Bauer. So how about we look at that proof? I don't know where the proof is. This is just talking about the SVD. And just its condition number. Well, nothing here about the uniqueness of the SVD, so let's just forget about it. Let's just remember this theorem. The left and right singular vectors are uniquely determined if the sigmas or the singular values are distinct, right? So the reduced SVD, what is a reduced SVD? Yeah, instead of here, we just reduce it. For example, instead of this being a square matrix, this is just the reduced SVD. Yeah, it's nothing too big here, nothing too much. SVD versus eigenvalue decomposition. Okay. So SVD expresses a matrix in proper basis for domain and range space to represent it as a diagonal matrix. Yes. We have seen something similar with eigenvectors. A non-defective square matrix A. Start recording. A non-defective square matrix A can be expressed as a diagonal matrix of eigenvalues if the range and domain are presented in the basis of eigenvectors. Range and domain. The basis of eigenvectors. Okay. So what about this? So there are fundamental differences between the SVD and eigenvalue decomposition. SVD uses 2 different bases. The left and right singular vectors, that's just, there are 2 different bases. The u and v are different bases. Eigenvalue decomposition uses just one eigenvector's basis, that is just the x. SVD uses orthonormal basis, whereas eigenvalue basis generally may not be orthonormal. That's fair. Not all matrices have an eigenvalue decomposition, but all matrices have a singular value decomposition. Every matrix has an SVD. Not every matrix can be eigendecomposed. Typically, eigenvalues tell us something about the behavior of the iterative processes that solve the matrix A, such that A to the K, A to the TA, E to the TA. Singular value tends to tell us something about A itself. So singular value is very fundamental to the matrix A. That's all. So the matrix A is of dimension m cross n. P is the minimum of mn, and R is always less than or equal to P. non-zero R, which is the rank, is the number of non-zero singular values of A. We now list how the SVD is related to fundamental. Yeah, let's see how they is related to the fundamental properties of the matrix. The rank of A is R, the number of non-zero singular values, like just as I said. The range, column space, of A is just the span of this. So column space is the span of U, and the kernel is this. Let's see. So if A was M cross N, then my U is a M cross M matrix, right? My sigma is an M cross N matrix, and my V is an N cross N matrix. So if my span, if it only has a rank R, then span of A will have a dimension of R. I mean, it only has R linearly independent vectors, right? Each of dimension M cross 1. So my first R columns in my U can give me the span of A, right? Right. And the kernel is this, the span of V R plus 1 to N. Now what is the kernel of a matrix? Let me look it up. So kernel of A kernel of matrix A is such that AX equals to 0, right? Kernel of L is all of the inputs such that L of V is 0. So all of those X's which give me 0. So now if I put U sigma V Hermitian X equals to 0, what can I say about this? About the kernel space here. So obviously the span of my matrix A is R, right? So if my matrix my matrix is of size M cross N, so M dimension, N columns. So my kernel, if my range consists of R, my kernel will consist of N minus R linearly independent vectors, right? N minus R, yeah. N minus R. So yep. It makes sense to me, although I need to do some more understanding about this. Why R plus 1 to N? If I write my matrix A as U1 sigma 1 V1 transpose plus U2 sigma 2 V2 transpose up to, let's say, UR sigma R VR transpose. Is this correct? Can I write my matrix A like this? According to this, I can. Like this is. Well, let me think. Can I even write it this way? Here. Kernel is all x such that Ax equals to 0. If this is my U, this is my sigma, and this is my V transpose. So U1, U2, sigma 1, sigma 2, sigma 3, sigma values. V1 transpose, V2 transpose, V3 transpose, right? So let's apply this to here. Let's just multiply this and see how my matrix turns out. U1, U2, U3, all these columns. Sigma 1 times the, so this becomes my first row, first column. Let me multiply the first row, first column. This becomes sigma 1 times this, sigma 1 times the first element here, sigma 1 times the first element here, and the rest is all 0. First row, second column. So this becomes just sigma 1 V1, this entire thing, sigma 2 V2, this entire thing, transpose here, sigma 3 V3 transpose. All the third elements are multiplied. Okay. This is it. Now I multiply my pre-multiply with U1, U2, U3. This is my entire matrix. How do I do that? According to this, according to my slides, AQ, which is the Q rank approximation of this, is just, as you can see, it's just the multiplication of U and V with their sigma. So obviously my matrix A should have been written in this form, should be capable of being written in this form. From here, I'm unable to go to the next step. Or is it just how matrix multiplication is defined? Can I say this is how matrix multiplication is defined? Just multiply the product of the first column with the first row, second with the second row, third with the third row. But there should also be one state where the first column is multiplied to the third row, right? When will that be? That will be, let's say I want to get the my first element is just this, the first row multiplied with the first column here. So that is the first element of U1, right? Let me write that way. Let me write this as the matrix. This I write the matrix U, and this I will write my new matrix as, let's say, P. Okay. So UP is, let me just write the first element, or let me just write the, first element. First element is U11, P11, then U12, P21, then U13, P31, and so on. My second is U21, U21, P11, U22, P21, right? So now okay, let me not write it this way. UP, so the ijth element here is sigma ith row of U, P, J, so sigma U I K P K J, sum over all K, right? Sum over whatever K is possible. Let me write UP is A and Aij is this. Now what I want to write this as, now if I want to write this as, let's say the first column multiplied with the first row, right? Multiplied with the first row, then the second column multiplied with the second row transpose. So let me write the first, this one. This is equals to what? The first column, yeah, so the ijth element in this is U1 I P J1, right? That's just what happens, right? If I multiply the first row with this one, all of the ijth is ith element of this and the jth element of this. That's just multiplied, right? Yeah. So now if I sum this for 1 and for 2 and for 3, I don't see getting that actually. This becomes U1I Pj1, U2I Pj2, right? U3I Pj3, adding these. How does that become this? Something is not correct here. Anyway, I'm going to skip that. So the two norm, I'm going to skip that. I don't know, that's, maybe I need to study that. The definition of matrix product, I guess. Or why, let me, yeah, when I get to the next slide, maybe just look at, let me just look at internet and find out on the internet. So the 2 norm A is the first singular value and the Frobenius norm is the square of addition of all singular values. This I can prove. For square A, determinant A is product of all singular values. The non-zero singular values of A are the square roots of the non-zero eigenvalues of, okay, so non-zero singular values of A are the square root of the non-zero eigenvalues of A Hermitian and A Hermitian. Okay, this can be proved. So A Hermitian A is just putting that together, and this is just V square of that thing. V Hermitian, and these are orthonormal. So these are like the eigenvectors, eigenbases, and the inside one is the square. Okay, fair enough, whatever. Representing matrices by sums of rank 1 matrices. Yes, now this is the, yeah. Represent A as a sum of M rank 1 matrices, okay. There are many possibilities. Let J contain the jth of the M rows of A. Let J contain the jth of the N columns of A, okay. Let Aj contain one of the Nn entries, okay. What is the property of some representation that we would like to see in numerical analysis? Right, this statement I still do not build. I'm having trouble getting into this. Or is it just how singular values are defined? According to them, A is sigma uj, sigma j uj vj transpose, j going from 1 to r, right? But instead, really what happens is you have a u here, you have a sigma here, and you have a v transpose here. Right? Let's say sigma v transpose, I combine them to write a one singular sigma v matrix, sigma v transpose matrix. You know, all these rows are multiplied with that particular singular value. Now my question is why? Why is this true? Why do I just need to multiply the first column with this one and it will be a rank 1 matrix, and the second column with the second row, and the third column with the third row? None of my first column multiplied with the third row. Those terms are not there. This is something that I do not understand. Anyway, let's assume that is true for a moment. I'll get to it now. If AQ is the best rank Q approximation of A in the 2 norm, then yeah, I mean AQ is the best rank Q approximation of A in the 2 norm. How did they prove this? A is U sigma V transpose, sigma U V, yeah, A minus AQ is sigma Q plus 1. Yeah, so the residual is yeah, so anyway, if I were to do it a rank Q approximation, so the first singular value which is left out is the residual here. So if this is AQ, then A minus AQ in the 2 norm is the sigma Q plus 1. Let's see the proof now. So I have to prove these two statements. If A minus AQ is I going from Q plus 1 to R, sigma I U H, right? I'm still assuming that, oh wait, let me first see why this is true. Singular value as rank 1 matrices. I've got something here. Let's see. U sigma V transpose X. If I write my, yeah, this is fair. V transpose X, X comes inside. Yeah, sigma's inside. That's fair. This step from here to here. U times UK VK transpose okay, let me write it. Maybe I do not understand it very much. U times this sigma 1 V1 transpose X, sigma 2 V2 transpose X, sigma 3 V3 transpose X, and U here is U1, U2, U3. Okay. So I'm sorry about that. I still do not understand this. I still do not understand this actually. How did they get from this step to this step? I mean, all he said is this, just this holds. I mean, yeah, but probably for them, why not for me then? Why is this just the first column multiplied by the first row and the second column multiplied by the second row? Why is there never an instance of first column being multiplied to the second row? Let me look for Okay, let me do this then. Okay. So first element of this multiplied by the first. So this will just give me a, this will give me some matrix. And what will that matrix be? Matrices are applied to columns, you know, not to rows. This is why I am having difficulty understanding this. I don't care if this x was here. This is not making it easy. So matrix applied to a row. Let me just, you know, let me just, first element with the first element here. Second element multiplied, the second element in this will always get multiplied to 0, right? All of the second onwards, all of the elements. So this just becomes, okay, this just becomes u1 sigma 1 v1 transpose. Okay, okay, now I understand it. Yeah, I'm being stupid here now. So let me just make it very, very clear to myself. Why was this not obvious to me before? I do not understand. First column multiplied to the first, and then second to 0, and then second row. So for example, let me just, you know, make it very precise. The element 1 comma 1 is the first row multiplied by the first column. So that only has the first row of this. So the first element of u1 multiplied by the first element of v1, and then all of the next ones are 0. So u1 first element multiplied by v1 first element, rest of all 0. Let me look at n cross 1. So the last row of this, the first row of this, the last row of this, the first row of this, again the first element of, sorry, the last element of u1 multiplied by the first element of v1. Let me look at the 1 comma end row. So 1 comma end will be the first row of this and the end row of this. That will again be the first element of u1 multiplied by the last element of v1 end, and here it will be u1 end, v1 end, right? Rest of all are 0. How about a middle element? Let's say mid comma mid. So the mid row of this and the mid row of this. So just the mid element of here multiplied by the mid element of here, and all the rest are 0. So it is just okay. Yeah, okay, now I understand it. So okay, now we can get to the proof. I think, oh man, now we can get to the proof. I understand it now. I think it is clear to you as well. Sigma, well, A is sigma j uj vj transpose. All of these rank 1 matrices add up to makes sense. Okay, finally. So A minus AQ is just the everything after Q Yeah, everything after q can be represented like this. Sigma q plus 1 is always greater than our singular values of a minus aq. So a minus aq 2 norm is sigma q plus 1. Okay, because the 2 norm of a matrix is just the first singular value, and the first singular value for this a minus aq is sigma q plus 1. Okay, so that's true. Next, suppose there is b such that rank of is less than equal to q, then a minus b2 norm is less than equal to a minus q2 norm, which is equal to sigma. So something which is a better approximation of a than aq, right? So if b is so rank less than q and null space. AW2 norm is less than sigma q plus 1. Okay. So AVI for some VI, AVI is U sigma VI, U sigma. Okay, just that one vector. So UI sigma I, right? Spanned by V1 to VQ plus 1. Z is alpha vi to q plus 1. Norm of z is alpha square. Az is alpha I. Yeah. What are we trying to show? Norm of AZ is, this is 1, is always greater than equal to sigma q plus 1. How? Well, sum of, you're trying to get to a contradiction somehow. So yeah, the pseudo, let me get back to that, but before that let me skip ahead and complete this and get back to it again. Pseudo inverse, just one thing left to prove, that this is the best approximation, is the minimum. Yeah, this is just a pseudo inverse in which we have the matrix inverted. So U sigma V transpose was the matrix. I just want to inverse that. And such, what matrix will invert that? V sigma inverse U Hermitian. But sigma inverse does not exist because it's not a square matrix. So instead of sigma inverse, I have a sigma plus, where sigma plus is just all of these singular values inverted, and this A plus, this Moore-Penrose pseudo inverse is the best, is the one which we get if we want to solve the least squares problem. That's the best approximation. Let me skip and see what's the next thing that is here. How to compute the SVD. Okay, yeah, we can do it in the next video. So for now, let's look at this proof then. Okay, I understand. I think I understand the proof. Let me try to do it. The proof is by contradiction. Let me assume there exists a B such that A minus B norm 2 is less than sigma q plus 1. There exists a B where rank of B is less than equal to q, right? Because I wanted to find the best rank q approximation. So let's say there exists a B where rank of B is less than equal to q. Okay? Yeah. And A minus B norm is less than this. Okay? So this is this is what I want to prove. Now, as B is a complex with rank less than q, rank less than q, that means there is an n minus q null space. So there exists a null space of dimension n minus q. But the point is that B spans all of q dimensions, right? All of the q rank that B is, right? So it has n minus q null space. The idea is that I want to show right. So this is what I want to show. Basically I want to get to a contradiction, but any q plus 1 method So what I want to show is that any vector, any space which is spanned by q plus 1 See, here's the, forget it. Let me just look at this look at the sketch at what's happening. Basically, we first show that AW norm 2 is less than sigma q plus 1. Then we look at a Z which is spanned by q plus 1 vectors. And we look at AZ which is just sigma u alpha I. And we look at the norm of AZ in order to try to get a contradiction here. And the norm of AZ will always be greater than sigma q plus 1. Well, that cannot be possible, right? So yeah. So that's a contradiction. But then let me what I will show is that for any vector Z which is spanned by V1 to VQ plus N, VQ plus 1, YQ plus 1. YQ plus 1. Well, computing the SVD, which is the next video. Fuck this shit.